In this lesson, we're going to focus on WireLevel security, so let me begin with a short demo. You can see in my bash shell, I'm about to run a Java program called Google Client. This client makes a GET request against Google, but it uses HTTPS instead of HTTP. As part of the peer authentication phase, so that mutual challenge phase, Google is going to send my way 3 digital certificates. These digital certificates are, in effect, vouchers for its identity. We'll get into some detail in a bit, but let me begin by running the demo. So you can see that the status code return is 200. That signals, as usual, a successful GET request. Then you see Cipher Suite, and there's an inscrutable-looking phrase on the screen. We'll go through that in some detail momentarily. The short version is that this summarizes all of the algorithms at play in setting up this connection. What then follows is some information about each of the 3 digital certificates. You can see, for example, that the type of each certificate is X509, and that's basically the current standard for digital formats. You see a hash code, that's sometimes called the fingerprint. The algorithm in all cases is RSA. This is a well-known algorithm, public key algorithm, more about that later. And then the certificate type and the format turn out to be the same. Now, let me move to one of the working files. This is called WireLevel.txt, which basically does a summary of what's happening. So let me start with the digital certificate, which plays such a central role. This, by the way, will be our first, not our last look at the digital certificate. So for our purposes, there are really 3 fields of principal interest in the digital certificate. The first is this. The certificate contains a public key from a key pair. For right now, I'm just going to depend on your intuitions about key pair, although we will get into details about that as well. So the public key, as the name suggests, is a key that I would feel free to distribute. Amazon has a public key. I can have a public key. It's basically an identifier. There's a digital signature from a so-called certificate authority, abbreviated as CA, and well-known certificate authorities include RSA. We've just seen that from the algorithm, and VeriSign. Basically, a digital signature is an encrypted hash value, and as the name suggests, it's meant to be the counterpart of a physical signature that you or I might use. The important thing is that digital signature is a voucher for the public key. So in effect, on the Google digital certificates, there's a signature that vouches that those certificates are in fact identifiers of Google. Finally, there's a hash value, usually called the fingerprint, that identifies each certificate. So each certificate is going to have its own fingerprint. Now, there's some other fields of interest. In particular, there is a from and to. So, for example, a typical digital certificate might have valid dates that span 3 years, let's say. But you could have ones that are longer, ones that are shorter. Now, here's the gist of the role that the digital signature plays. During the peer authentication phase, which is basically the first phase in the so-called HTTP handshake, one side, so in my case, this is my Google Client program, is going to challenge the other side, in this case, let's say the Amazon web server or the Google web server or whatever, to produce one or more digital certificates. As it turns out, Google is not going to challenge my client. Amazon wouldn't either. And again, we're going to let that pass for now. So the peer authentication turns out to be one-way authentication. It's basically the server, Google, authenticating itself to us by sending us 3 certificates. Now, in order to validate that certificate, the challenger, so my Google Client program, needs to check that certificate against what's called a trust store. And as the name suggests, a trust store is just a list of all of the digital certificates that the challenger trusts. As it turns out, Java, core Java, ships with a default trust store. You see it down here. It's Java Home, JRE, Lib, Security, CA certs. Certificate Authority Certificates. So that's the default trust store. It's basically just a file, in this case, on the file system. One important point is this: the verification of a certificate might be indirect. Suppose, for example, that this is a fresh computer. I've never done an HTTPS connection against anybody, and I go the first time against Google, and let's say my default trust store does not have a Google certificate. However, the Google certificate has a digital signature from, let's say, RSA. RSA has a digital certificate. So basically, what would happen in the verification is that the signature would be verified. And if the signature turns out to be legitimate, we assume that the digital certificate on which it occurs is also legitimate. So the long and the short of it is, on my side, the client side in this case, all three of those Google certificates are being verified against this particular trust store. Now, as noted, and as the name emphasizes, in peer authentication, each side typically challenges the other, but when you hit traditional websites such as Google or Amazon, typically the peer authentication turns out to be one way. The client challenges the server, but not the other way around. In web services, by contrast, it is common to have genuine peer authentication. Each side needs to provide a certificate, at least one, to verify its identity to the other.